All right, now let me begin by sharing my screen here. So we're going to begin in section 2.3. Section 2.3 is the idea of the inverse of a matrix. Now, before we actually talk about the inverse of a matrix, let me go to uh, my notepad and just want to illustrate something that's very similar to what we're going to be doing here. Share and my notepad. Okay. And again, as I go through from screen to screen, if something doesn't look right, please let me know. All right. Now, something in the way of algebra. So we're not talking about matrix. In a moment, we will. But let's just say this is some kind of an algebra concept. What I'm trying to do is tie in what we're about to see to our algebraic expressions. So let's say I have a simple linear equation. And these are not matrices. These are just algebra. Think algebra. And I want to solve for x, right? And of course, we say, well, divide both sides by a, assuming a is not 0, and that solves it, right? But we're going to do this slightly differently, okay? So, well, to divide by a, so this is what I'm thinking, x is b over a, and we're done, right? That's the answer. But we're going to actually take a couple of steps to get there. So notice in here, I'm dividing both sides by a in order to solve for x. Well, rather than dividing by a, I could think of, not that we do it this way ordinarily, but I can think of multiplying the left side by inverse of a, right? 1 over a, and that times x. But then whatever we do to equation, we got to do to both sides. So I'm going to multiply the right side by a inverse. And now on the left side, we know that a inverse, right, a to negative 1 times a is just going to be 1, correct? That product is 1. 1 times x is x, and the right side is simply a to negative 1b. And again, ordinarily, we don't solve it that way, right? We just say divide both sides by a, but we could rethink it in this term. Well, this is exactly what happens to the inverse of a matrix. So let's actually define what we mean by inverse of a matrix. So the inverse of a matrix, and again, if you have any questions along the way, please everybody ask. Otherwise, I'm just going to continue on. So we're going to talk about the inverse of a matrix now. The inverse of a matrix. So if A is an n by n, a matrix of order n. Now here, when we say n, this means n by n. In other words, we're talking about a square matrix. Okay, it's just a notation. So A sub n means a matrix of order n, an n by n matrix. Suppose that we have A sub n, and it is going to be what we call invertible. So A sub n is invertible, or we can also call it non-singular. Non-singular means just that, means it is invertible, means it has an inverse. So A sub n is invertible when there exists another matrix of order n, so same size, such that, so now we have a second matrix here, such that when you multiply AB, that's the same as product of BA. Now remember, these are square matrices, right? So multiplication is defined either way. Last week we said the multiplication AB in general may not equal to BA and may not even exist if you switch B and A. But in this case, because both matrices of our order n, so multiplication in either order will be defined. And so if we multiply them in either order and we get the identity matrix of order n, then in this case, we're going to say that B is multiplicative multiplicative inverse of A. So that's what the inverse of a matrix is. So right now we're using B as the multiplicative inverse of matrix A. Now, if this matrix B,
What does it say? I'm a little bit behind. Sorry if I'm interrupting.
no problem.
It says inverse of A matrix, and you have the two dots. Is that a dot after, and is that an end? Like it says N means,
All in here, yeah, I
yeah.
just have like an open circle,
Oh, that's an
and
open circle. That's
yeah,
an N. All
yeah,
right. And then just a question on the parentheses. I mean, never mind. After the parentheses says when there exists. Is that a there
yeah.
and cursive?
When there exists.
Okay, that's cursive. Yeah. All
Yes,
right. Sounds
thanks
good.
for asking.
Thank
No
you.
problem. Please, thank you for asking, Jesus. Anybody, if you can't read what I'm writing, please ask. Otherwise, I assume it's legible and readable. So hopefully everybody's okay now. All right. So again, B is called the multiplicative inverse of A. Now, if this matrix B does not exist, so if B does not exist, then in that case, we're going to say matrix A is singular. That's just another way of saying the inverse does not exist. Matrix A is singular. Now, the notation, we're going to let A, its superscript -1, represent B, which is the inverse. So in other words, from now on, as we go through this text, this book, through the lectures, we're going to use A superscript -1 as the inverse of matrix A. Okay, so that's just the notation. This is the notation for matrix inverse. So hopefully, again, everybody okay so far? All right. Now, let's talk about this theorem now. This is theorem 2.7 in your book, by the way. Theorem 2.7 talks about the uniqueness of the inverse matrix. So if the matrix exists, now, and by the way, not every square matrix has an inverse. I'll show you a couple examples where we cannot find the inverse, but this theorem tells us about if the inverse matrix exists, it's going to be unique. Now remember, unique means there's only one of. So for instance, here's how this theorem is going to go. If we have a matrix of order n, remember these are square matrices. Everything in this section is a square matrix. If this is an invertible matrix, in other words, if it does have an inverse, then a inverse, the matrix, the invertible matrix, the inverse matrix is unique. And again, in mathematics, when we say unique, means there's only one of that. It is unique. So let's take a look at the proof of this. We're going to prove this statement. So if an is invertible, we want to show the inverse is unique. Now, we're going to use proof by contradiction. Okay, so here's what we're going to say. We're going to say, suppose A has two inverses, right? The theorem says it's unique. We're going to say, well, suppose it has two, and by two, we mean two different. Let these be two different inverses, and call them B and C. So remember, we are supposing that those are different. Now, by definition of inverse, wouldn't I, when I multiply A times B, remember B is the inverse for now. When I multiply A times B, and we had it up here, A times B will give me the identity matrix, right? So if I do AB, I'm going to get I. Okay. Now, in this equation, I'm going to pre-multiply both sides by matrix C that you see. That matrix C, I'm going to pre-multiply both sides by that. So I'm going to do C times AB, and I'm going to multiply the right side on the left of I by C. With matrix multiplication, when you have an equation, folks, if you pre-multiply here by C, means you do it before AB, you cannot do post-multiply on the other side. It has to be done in the same direction. So if I pre-multiply, I have to pre-multiply here, which is what I've done. Now, using the associative property of multiplication, I'm going to group C and A together, okay, and then multiply that by B. And on the right side, remember, any matrix times the identity matrix is the matrix itself. So on the right side, I'm just going to get C. Now, on the left side, what is CA going to be, this product? If C is the inverse, what do I get when I multiply inverse of A by A?
I think you would just get the B, because I think the inverse and the regular of it would just cancel out, I think.
Sure. And that kind of cancellation in matrix world means they multiply to the identity matrix. With numbers, it would be like multiplying by a reciprocal. You get 1. In case of a matrix, when you multiply an inverse by A, you get the identity matrix. So again, in a way, it's kind of like cancellation, but it's more of multiplying to 1. They multiply to 1. Now, when I multiply the identity matrix times B, what do you think that product would be? The product of any matrix and the identity matrix is the matrix itself. So we get B is equal to C, correct? Now, look at this and look at our supposition. Didn't we say suppose two inverses B and C represent two different inverses? But in the end, we show that B and C are equal, right? That means these are not different. So in other words, we have reached what they call a contradiction. It contradicts our supposition. So we have a contradiction. Therefore, we prove by contradiction that B and C must be the same. So that means these cannot really be two different inverses. They have to be the same, which proves the uniqueness of the inverse matrix. Everyone okay with that proof? All right. Now, once we've done that, let's make some notations here. Let's note a few things. Or note. For example, if you multiply a matrix times its inverse, it's the same as multiplying the inverse of the matrix by the matrix. So matrix multiplication of a matrix, any matrix by its inverse, gives you the identity regardless of the order of multiplication. Okay. Now, here's another note. I mentioned not every square matrix is invertible. So here's matrix A. This matrix 2, 4, 6, 12 that I made, this one is not invertible. Not invertible. And we'll see later on why it's not. I'm just giving you examples, and you can run it by a software and try to find the inverse. It tells you it cannot be done. Here's one example. Here's another matrix A. This one, this time I'm going to go, let's say, 2, 1, 20, 10. This one also not invertible. Now something invertible. Something you probably notice about both of these matrices is that if you look at the second row of this first matrix, second row, when I made this up, I just randomly picked 2, 4, but I multiply that row by 3. See, I get 3 times 2, 3 times 4. So that is not going to be, I know that's not going to be invertible. For this one, I have 2, 1. I multiplied 2 times 10, got 20, 1 by 10 got 10. So this column is twice this one. Again, this is not going to be invertible. The whole matrix, both of these are not invertible. Okay. Now, let's see. So how are we going to find this inverse? Okay, so let's talk about that. In order to find the inverse, we're going to actually solve a system of equation, ax equals I. And then we're going to solve this for x. Okay, and once we solve for x, because remember, a times x is identity, so x must be the inverse. Therefore, x has to be a inverse. So what does that mean? That means in our system, let's say I have a matrix A, I want to find its inverse. Remember, these are square matrices. Everything in this section is a square matrix. So I'm going to adjoin A. This is just a line. And this is the identity matrix I, order n. So if A is 4 by 4, so is I. And then we're going to go through here, go through Gauss-Jordan, and reduce matrix A using Gauss-Jordan. Remember, when a matrix is in row echelon, it's going to be the identity matrix. It's going to look just like the identity matrix in its reduced row echelon form. So this matrix will be transformed into I to the left of the slide. And the right side, whatever that matrix looks like, this is going to be the inverse of A. And again, we'll do plenty of examples tonight. You'll see, hopefully it will clarify these for you. Okay, so this is how we're gonna do this. So in other words, to find the inverse, we're gonna adjoin the identity matrix to the coefficient matrix. This is called the adjoin. Let me write that. We're going to adjoin the identity matrix with the matrix of the coefficients A. And this A, by the way, it's going to be a matrix that comes from the coefficients on the variables for the system. Because remember, we're solving systems of linear equation in this course. So A is matrix of coefficients that comes from the system.
I had just a quick question about that.
Yes.
So, so that little like the line between the A and the identity matrix is the adjoin.
Yeah, yeah, I'm sorry.
And no, it's okay. So, and then you were saying that the A is gonna be not like the full I don't remember what it was called. You just said it like it's not gonna be like the full, like it's not gonna include the equals like
You got it.
numbers. It's just gonna include like the first things.
Yes, ma'am.
Okay, thank you.
Yeah, you're welcome. So for example, let's say I have a system, and we'll see, we'll get to solving a system, but real quick, let's say I have 2x1 plus x2 equal 4. 3x1 minus 3x2 equals, I don't know, 13. We're not solving anyway. So in order to solve this one, we're going to write it as ax equals b. Okay, now how do we write A? A is a matrix of coefficients 2, 1, 3, negative 3, correct? That's just A, matrix of coefficients. B is the matrix of constants, the column vector of constants for 13, 2 by 1. This is 2 by 2. And of course, X is just a matrix of our unknowns. This is also a 2 by 1 column vector. So the system in matrix is in the form AX equals B. So how are we going to solve this system in a few minutes? X, the solution to X is going to be, let me go back up here a step. We're going to pre-multiply by A inverse. It's going to be A inverse B. A inverse A, that's just the identity matrix. An identity matrix times any matrix is the matrix itself. So the left side is just X. The right side is A inverse B. So in order to solve the system here, you see right in here, this is the inverse. We need to find the inverse of this matrix. Once we do, we multiply by matrix of constants. That's what this is, constants. And then we have the solution that will solve the system. So that's kind of what's on the agenda for the exercises. We're going to be doing this for sure. And you will see, we can even do it for this made up example, but we need to see how we're going to find the A inverse in a moment. And are you okay, Jordan?
Yeah, I am. Thank you.
Oh, you're welcome. So everybody hopefully okay? All right. Now, so we're going to put this on hold. And this part, the adjoint matrix that we go from here. Let me also, you may say, well, can you write a line I for this example? Sure. So a line I looks like this. 2, 1, 3, -3. Remember, this line is an invisible line. When we go to Symbol Lab doesn't put a line. This is for us. Again, this means that we are adjoining this identity matrix with matrix of coefficients. So on this side, I'm going to have an identity matrix of order 2. And then we can go through Gauss, Jordan, and we go to Symbol Lab for that, Gauss, Jordan. And on this side, because I don't know what the inverse is, right? In a moment, though, we'll find the inverse of this in a moment by hand. And then I can fill in what's on this side. But the theory says, once you go through Gauss, Jordan, what moves to the left of this line is going to be identity. It's not really going to move, but because of Gauss, Jordan, the left side is going to look like this, folks. And the right side, right now, I don't know what it looks like. I'm just going to call it A inverse. There you go. This is what we're shooting for, what we're trying to find. Okay, so that's kind of where we're going to go. We go to Symbol Lab in order to do that step. And let me put a question mark. That's what we want to find out. Because once we have that, our next step is to multiply it by B, and then that solves the system. Okay. If everyone's good. Now, let's take a look at a note here. For a 2x2 matrix, a matrix A is 2x2, and let's say this matrix is going to be in general of the form A, B, C, D. These are just numbers, any number A, B, C, and D, whatever you want them to be, real numbers. To find the inverse of this matrix, there is actually a formula for a 2x2. Okay, the 2x2 formula looks like this. You go 1 over, we multiply the diagonal of A and D together. So it's going to be A, D, and then minus, we multiply the off diagonals B, C. Okay, so that's that part. And then the matrix A, we're going to switch A and D. So here's D, here's A. And then we're going to change signs on B and C. So this is the formula for finding a 2x2 inverse. Please keep in mind, Symbol Lab is what we want to do. The reason I mentioned this because it's quick, not hard to, I hate to say memorize, but not hard to remember. And it works, and the book mentions it. So that's why I mentioned it. Otherwise, we do this in Symbol Lab. So for the example I have, let's do this for our made-up example. Here it goes. So my A inverse will be, first of all, What are the A, B, C, Ds for my made up example? A is 2. Remember, A, B, C, D. So it's going to be 2, 1, 3, -3. To find the inverse using the formula. So I'm going to have 1 over. The formula says multiply the diagonals. That's 2 by -3, that's -6. Then we subtract the product of 1 by 3, that's BC. 1 by 3, that's 3. And then in here, we're going to have a 2 by 2 matrix. AD becomes DA. We swap them. That means 2, -3. We're going to swap them. It's going to be -3, 2. The off diagonal, this is diagonal. These are off diagonal. The off diagonals, notice BC becomes -B, -C. So that means I just change signs on 1 becomes -1 and 3 becomes -3. Now here's the inverse of the matrix. Let's finish this off. First, the fraction in front, -6 minus 3, that's -9. So it's like multiplying this matrix by -1/9, isn't it? Because I have 1 over -9, that's -1/9. So I'm going to multiply -1/9. Remember the way the constant scalar multiplication, scalar multiplies by a matrix, you multiply every element of the matrix by the scalar, by the constant. So it's -1/9 times -3. That's 3/9 or 1/3 positive. -1/9 times -1, that is 1/9. -1/9 times -3, that's 1/3. -1/9 times 2 is -2/9. And there we have that one. So this is indeed the inverse of this matrix. Now, the solution to my made-up example, x, is when you multiply the inverse, that's 1/3, 1/9, 1/3, -2/9. It's when you multiply this by the matrix of constants, 413. And there you go. So how is this going to multiply? Well, I'm multiplying a 2 by 2 times a 2 by 1. If you recall the multiplication, the way it works, the inside numbers must be the same, and they are. The outside numbers gives you the dimension or the size of the result, the product matrix. The matrix we're about to write is going to have 2 rows, 1 column. It's going to be 2 rows, 1 column. So I'm preparing for 2 rows and a column. The number in this spot is going to be first row, first column. So we're going to multiply first row by first column. So 1/3 times 4, that's 4/3, plus 1/9 times 13 is 13/9. The number down here is going to be in the second row, first column. So I'm going to multiply second row by first column. 1/3 times 4, that would be 4/3. Negative 2/9 times 13 is 26/9. And then we can do the arithmetic. Let's see. 4/3 plus 13/9, 4/3, the LCD is 9. So I'm going to multiply top bottom by 3. That's 12/9. 12 and 13 is 25/9. Please verify. So that's the first number. That's the solution to x sub 1. And then 4/3 negative 26/9. Again, 4/3 multiply top bottom by 3. So I have LCD. 3 times 4, 12. 12 minus 26 is -14. negative 14 ninths, and that is the solution. Sorry, I know it looks a little, let me magnify this for you. Hopefully you can see a little better. And there you go. So in order to solve the system, to make a long story short, we need to be able to find the inverse of the matrix. The matrix must be invertible. If it's not invertible, that means the system does not have a solution. So everyone okay on the inverse of the matrix? All right, I'm gonna remove this paper slowly. All right. Now, let's see. The next thing we want to talk about are some properties of inverses. Okay, so let's talk about properties of inverses. Properties of inverses. Now, to cite the properties, there's actually a theorem. A theorem, I believe it's theorem 2.8 in your book that cites properties of inverse matrices. Okay, now here are the properties. Suppose again, A order n is invertible. In other words, the inverse does exist. If it doesn't, what we're doing doesn't make sense. If A is invertible matrix, and let K is going to be a positive integer. Let K be a positive integer. And a constant different from 0. That's what C is. So when that's the case, then we got 4 things here. 1, if you take the inverse of the inverse matrix, what do you think is going to happen here? I'm doing inverse of an inverse.
They cancel each other?
You got it. It's like multiplying -1 times -1. They cancel, so you just get the matrix A back. Item number 2. If we have A to the k power, remember k is a positive integer. So for example, let's say I'm going to square a matrix A times A and then find the inverse. In order to do this, I could square or raise it to a 3rd power, A cubed. A cubed means A times A times A. And I want to find the inverse of that A cubed. Well, we can do it by doing A inverse times A inverse, K times. So it's going to be A inverse to the kth power. So what it looks like is that you can switch the K and -1. So you can raise A to a power, find its inverse, or find its inverse, then raise it to a power. So that's property number 2. Part 3 of this theorem. If I have a constant multiple of a matrix, and we want to find the inverse of that, remember, if C is a constant, so C to -1 means 1 over C. It's like 2 to -1 is 1/2. That's what this is. And then times whatever the inverse of A is. Item number 4 is the last one. If you do inverse of a transpose, so suppose I have A transpose now, and I want to find its inverse. You can also do inverse of A and then transpose it. That property also holds. We will prove number 2 and 4 in just a few minutes here. But these are the properties of inverse matrices. Okay. Now, Well, let's see. Maybe we go ahead and prove one of these. Let's say I'm gonna prove item number 4. Okay. Let's say we want to.
Isn't just a question, isn't number 4 and number 2 the same? Or what's the difference? What's the difference between a constant, or is t a variable? So what that represents?
No. Remember from last week, T is transpose of the matrix.
Transpose?
Transpose, yeah.
Transpose.
AT is transpose.
And k is just a constant?
Right. A is a constant. So for example, A cubed. Here K is 3.
I'm referring about the k part. Oh,
yeah.
Never mind. I see.
No,
I heard wrong.
Yeah, so that's K, the role K plays. K is a positive integer here. T is transpose. Remember, for example, suppose I have 1, 2, 3, 4. This is A. A transpose is when you switch the rows and column. Row become column, row becomes column. So there you go. That's A transpose. A transpose. The number 4, so we want to find inverse of transpose of A. Okay, so let's actually prove number 4 here. Okay, I believe this is one of the exercises. This is like exercise number 66, I believe, in your book. So we want to prove item number 4 here. So to prove number 4, well, to prove, here's our strategy to prove number 4. We must show, this is like the thought process. We must show that product of AB is I and BA is I, right? Remember, either order, whether I multiply A times B, B times A, I get the identity matrix. This is by definition of inverse. So let's do, first I'm doing something like AB at the moment. So I'm going to say, I'm going to multiply A transpose times its inverse transpose. Okay, I'm doing like AB here. I need to show this is identity. Now, they're using properties of transpose from last week. A transpose, A inverse transpose is the same as A inverse A transpose. This is from last week. Now, A inverse times A, isn't that the identity matrix? Inside parentheses, I have the identity matrix. So this is an identity matrix order n, and it is being transposed, right? That's within parentheses. And what is the transpose of the identity matrix? Here is 1, 0, 0, 1. What's the transpose of this? 1, 0, the row becomes column. Second row becomes second column. Isn't it itself? Looks exactly the same. So the transpose of identity matrix is just the identity matrix. Either way, they're both identity. So we just showed the product of A inverse. This we just showed AB equal I. Now, let's show the other way, B times A. At this time, we want to show that A inverse transpose, this is like B now, the second matrix, times the first matrix. If these two matrices multiply to identity in either order, then they must be inverses of each other. So now this is, I'm doing B times A now. Second times first. Now this one, again, using properties of transpose from last week. I can write this as A, where you write A first, A inverse second, then transpose it. And AA inverse again is identity of order n. And when you transpose the identity matrix again, it remains as identity matrix. So we just showed a matrix times another matrix gives you identity. We change the order of product, we got identity. So these are inverses of each other. Therefore, A inverse T has to be AT transpose because it satisfies the definition of inverse. There you go. And that would be the proof of part 4. Okay. All right. Now, everyone okay on this part? Okay. Let's see. Now, what about we want to find the inverse of a product. So let's take a look at this next theorem, theorem 2.9. Now we're looking at the inverse of a product. Okay, so here's how this theorem goes. If we have two matrices, A and B, square matrices of order n, and suppose they're both invertible. Okay, so these are both invertible. Invertible. Okay, matrices. Now, according to this theorem, AB is invertible. And the inverse of AB is going to be B inverse, A inverse. Notice we want to find the inverse of a product. So this we're going to remember in future chapters, folks. The inverse of a product, it's product of inverses in reverse. That we're going to prove that in a moment. So AB inverse is not A inverse B inverse. That's
I just had a quick question about that.
Yes, Jordan.
So I remember, I don't know if it applies at least to this chapter, but so when you say like AB inverse equals B inverse A inverse, does the fact that it's BA matter and not AB?
Yes.
Because I remember, okay, so it does. Okay.
Yeah, absolutely. Let me write that. AB inverse does not equal A inverse B inverse. So that unfortunately doesn't work. That's why we have this theorem. And we'll prove this. I'll prove this for you. The proof is interesting. It's not difficult, but we'll see the proof of this. But again, it's kind of like the way the transpose works, remember? I had it, let me put this paper back here. You see the order of transposition here? When you go A inverse transpose, it's not going to be A transpose, A inverse transpose. It's going to be A inverse transpose times A transpose. You switch the order of these two and transpose them. That's exactly how the inverse works. It works exactly like the transpose does. Now, let's actually see a proof of this one. So here is the product matrix AB. Now we want to find the inverse, right? This is the inverse of product, right? The inverse of the answer is this. The answer is like, well, how do you know this is the answer? The inverse of this product is this, the right side. Now, it's kind of a wimpy proof the way we go about it. It's this. Here's AB. Now, if the right side is what they say it is, which is the inverse of the product, okay, then wouldn't I multiply these two And when I do, what am I supposed to get? I'm multiplying a product matrix times its inverse. Well, this would be a matrix, right? This is its inverse. Shouldn't I, in the end, get identity? A matrix times its inverse of a product is this. That's what they claim. When I multiply these two, I should get the identity matrix. Let's see if we do. Now, the way this product works, the way it's lined up, I'm going to change using the associative property of matrices. Remember, these are all square matrices of the same order. So multiplication is definitely defined. We don't have to worry about that part. So first, I change the grouping. I'm grouping these two. I choose to multiply BB inverse first. Now, what would I get? What would I get when I multiply B times its inverse? Any matrix times its inverse multiplies to
The identity matrix.
very good, the identity matrix. And of course, identity matrix times any matrix is the matrix, right? So this identity, you can multiply by A inverse, by A, doesn't matter. This goes away, doesn't it? The I? Because AI is just A. In fact, there you go. Because AI, any matrix times identity is itself. Now, A inverse, a matrix times its inverse would equal identity, doesn't it? It worked. So far, this works. Now, if we multiply, change the order of multiplication, if it works the other way around, then we're going to say, okay, then looks like they have the right inverse. So we're now switching the order of multiplication. I'm multiplying the inverse of a product times the product matrix. And let's see if we get identity. Because remember, any matrix, remember, let me write that. We said earlier, A inverse is I, and A inverse A is I. For any matrix and its inverse, this should be true. And that's what we are verifying. The theorem claims the right side is the inverse. So we're trying the inverse, see if it's working. So far, it's worked in one direction. Let's see if it works in this form, that form of the product. Now, change using associative property. We're going to change the order of multiplication. Going to go the two middle matrices, multiply A inverse A, and again, just like up here, any matrix, inverse times A is identity. B inverse times inverse is B inverse. And B inverse times B is identity. So we showed identity in both directions. The product matrix times inverse of product matrix, inverse of product matrix times product matrix. Both of these gave us identity. So yeah, looks like this is true. It works. So I'm just going to say, so it conforms to the definition of inverse. What conforms? The right side. This conforms to the definition. This was the definition. This times this should be I. This times this should be I. It conforms the definition. So the right side of this theorem, this has to be the inverse of the product. We're okay on that, everyone? Okay, we're almost done with this. And then we'll look at quite a few exercises, and we use Symbolab and make it a little more dynamic. Let's take a look at Theorem 210 now. This Theorem 210 is called the cancellation property. Okay, cancellation property of matrix. If capital C here, not little c. Remember earlier, little c was constant. This is a matrix. If C is invertible, means it has an inverse. Invertible matrix. And then, first part, if you do A times C equals BC. If you have this equation, feel free to cancel C. Then A is equal to B. This is called right cancellation. Right cancellation. Item 2 of this deals with left cancellation. So for example, if I have CA and that's equal to CB, then A should equal to B. This is canceling the C from the left. See, the only time this works is if C is invertible. Now let's prove this one. For example, let's prove number 2. You can see if you can prove number 1 on your own. Let's say proof of 2. For proof of number 2, suppose I have CA equals CB. Okay. Now, I'm going to pre-multiply both sides by the inverse. So I'm going to get C inverse CA and pre-multiply on the right side C inverse CB. And again, what is C inverse times C going to equal? Any matrix and its inverse. The product would be identity, right? So this is going to be an identity times A. This is identity times B. And that's just A is equal to B. So there you go. It's as if we canceled the C's. So you can try that with number 1 if you like. It's done similarly. If you get number 1, you start this way and multiply both sides on the right side of C by C inverse. And that should work out for you. So everybody okay again on this theorem? The right-left cancellation. All right. Now, let's finish this and we go to the exercises. Again, any questions, ladies and gentlemen? Are we good on what we have so far?
I think it's just we learned a lot of theorems in one go, so we're still digesting.
Yeah, I believe it. You're right. Thank you, Jesus. Okay, and one last theorem. One last theorem here. That one, let's try this one. This one has to do with systems of equations. Now, this is the last theorem of this section we're going to talk about. Theorem 211. Okay, this theorem says that systems of equations with unique solutions. Okay, let's see how theorem is stated. It talks about systems of equations with unique solutions. So suppose A is matrix A is invertible matrix. Okay, then the linear system, AX equals B, has a unique solution. And the solution is given by X is equal to A inverse B. Remember, we did one earlier when we talked about finding the 2x2 determinants. I mean, not determinant, I'm sorry, the 2x2 inverse. An example I did, the answer had fractions in it. So there you go. According to this theorem, if A is invertible, then the system has a unique solution, and this is the solution. So let's prove this one. Okay, so first of all, the uniqueness of the solution. Okay. Proof. I'm going to try to prove the uniqueness. So remember, anytime we want to prove uniqueness, we use most likely proof by contradiction, right? So here's how the contradiction is going to go. We're going to let x1, x2 be two solutions. And two different solutions, let's say. Okay, so I have two different solutions. Now, that means ax1 is equal to b, and on the other side, ax2 is b, right? If there are two different solutions, so that means this is a solution to that system, so is this one. That means I can write them like that. Now, what do we get from this? Well, b on the right side, this b is the same b here. So I can replace this b, see this b are the same, replace this by ax2. That means ax1 should equal to ax2, because that's what b is. Now in here, what do we do? Well, let's say we were told a is invertible. Since a is invertible, what can I do? Well, I have an equation. I'm going to pre-multiply both sides by the inverse. So A inverse A, x1, should equal to A inverse A on the other side, x2. The product of the inverse of a matrix and the matrix gives you the identity on both sides. Identity times any matrix is the matrix. Same thing on the right side, and we just showed the two are the same, but remember what we started with? We said to let these be different. We assume they're different. We show that then no, they have to be the same. They cannot be different, right? This means these are the same. So we have same, not different. So then there is a contradiction. So we prove this by contradiction. Because again, we assume they're different, and then we show that they cannot be different. They have to be the same. Now that's just the uniqueness part. Now the solution is given by, let's do the given by part. For the given by part, again, if ax is equal b, we can pre-multiply both sides by the inverse, and we get a inverse b. And A inverse A is the identity matrix times X is X. The right side, whatever it turns out to be. I did an example earlier, remember the one that had fractions for the answers, and that's exactly what we showed. So here's again in this theorem. So the theorem again shows the form of the solution. This is the form of the solution. And we are guaranteed that it's unique, provided matrix A is invertible. If the matrix A is not invertible, then the system could be dependent or inconsistent. We just need to explore that further. And usually what happens, we'll see in a few minutes, is that when we try to find the inverse, we're not going to get, remember the adjoint? We get I and then the line A inverse. That I matrix is not going to form. We get something like a row of zeros or something. We will not be able to form the I matrix. All right, so everyone okay on this work? If we're good, then let's take a look at some of these exercises in the book. So I'm going to move this and I'm going to change stop share. I'm going to switch to page of the book. Okay, so now we have this one. Went too far. Okay, I'm going to the exercises now. This is 2.5, 2.4, and 2.3. Okay. Wow, look at these systems. Huh, huge. All right, let's go back up here. Section 2.3. In the early exercises, it show that B is inverse of A. So for example, let's say I want to do, I don't know, number 4. We want to do number 4. How would I show? It says show B is inverse of A. This is inverse of A. How would I show that? If two matrices are inverses of each other, what do we know about their product? What would A times B be? Shouldn't the product be the identity matrix? True?
Yes.
Okay, so that's what we're gonna do. So I'm just writing this down right now, and then I'll show you how to do this, by the way, quickly. We're gonna use software to do all these multiplications and stuff. But I'm gonna do it by hand, and then we use the software. So let me switch back to my notepad. Okay, it says show that these B is inverse of A. So that means if I do AB, the product AB, I'm gonna get 1. Remember, it's gonna be a 2 by 2. 1 times 3/5 is 3/5. -1 times -2/5 is plus 2/5. First row, first column. And then the first row, second column. First, second. 1 times 1/5 is 1/5. -1 times -1 times 1/5 is -1/5. Second row, first column. Second row, first column. 2 times 3/5, 6/5. 3 times -2/5 is -6/5. This element is in the second row, second column. So I'm going to multiply second row by second column. That's 2 times 1/5, 2/5, and then plus 3/5, right? 3 times 1/5. Okay, now let's see. 3/5 plus 2/5, that's 1. 5th minus a 5th, 0. 6/5 minus 6/5, 0. 2/5 and 3/5, 1. We got the identity matrix. Okay. Now, BA ends up being also 1, 0, 0, 1, and I'm going to show you this one now using the software. So let me go change my share once again. We're going to use the software. I'm going to go to, where do I want to go to? Let's go to Canvas. All right. Now in Canvas, by the way, folks, remember I have these online matrix calculators. This is Symbol Lab. The one in the middle is Matrix Calculator. When you click on this link, when you click on the Matrix Calculator, then what pops up? There you go. This is what comes up. Okay. So I'm going to do B times A. I'm going to multiply a 2 by 2 times a 2 by 2. Okay. So that's matrix A. I'm actually doing BA in our exercise. I know the software here says AB, but ours is actually BA. I'm doing the one with fraction first. That was 3/5. So here's 3/5. And then 1/5. This one, -2/5. This is 1/5. Okay, so that's my first matrix. This other matrix, oops, this one is going to be in the exercises, that's matrix A. So it's going to be 1, -1, 2, and 3. Give you a moment to catch up. So I'm multiplying the matrix on the left times matrix on the right. The matrix on the left is matrix B in our work. And in here, see, it says A times B. I'm going to do A times B, left times right. And there it is right down here. This one, display decimal. See that? This matrix was our B. And this one was A. The product is the identity matrix. You see how that works? So we just showed the ABBA is equal to the identity matrix. So yes, they're inverses of each other. Everyone okay on this example?
Yeah.
Okay, thank you.
And
Yes.
I had just a kind of a question about, so I think I remember you saying something along the lines. So would we be able to use like these applications for during exams?
Of course, yes.
Oh, okay.
Please do. Yeah, definitely. We don't want to do any of these by hand, honestly. It's just not practical and it's pointless. Now, you saw me, I showed you how I did AB. It's like, oh, okay, I see how that's done. But imagine if you have to do all of these multiplications by hand, it's just going to be a nightmare. And you will see in the next section immediately tonight, maybe after the break, when we go to section 2.4, talk about elementary matrices, we're going to have a whole bunch of multiplication of these elementary matrices. We don't want to do them by hand. So please definitely use these softwares or any other software that you know of during homework and definitely on the exam. Yes, absolutely. You're free to use them. All right, so everybody good on this work? Now, if you're okay, let's see. Let me switch to the book. We do a different example now. Let's do this one. Okay, so I'm looking at the book. Let's take a look at exercise number 18, where we have to find the inverse. So in exercise 7 through 30, we're going to do number 18. Find the inverse. So there you go. Let's try number 18 together. Okay. First, I'm going to write this down on my notepad just so I have that. I'm going to call that matrix A. The matrix A, first row 3, 2, 5. The second row is 2, 2, 4. And the third row is -4, 4, 0. Okay, now we want to find the inverse. So anyone remembers how we said we're going to find the inverse? Let me, hold on, let me stop this share, go back to my notepad and just kind of show you what I'm doing here. There you go. I just wrote number 18 here. What do you think, how we're going to find the inverse of that? It's not a 2 by 2, so we're not going to be able to use that formula for 2 by 2. For 3 by 3 and higher, if anyone remembers how we're going to do this? Theoretically, we haven't done one tonight, but earlier with the 2 by 2, I did do it in the beginning of the evening. Anyone recalls? Here's a hint. Remember I said this is A, and didn't we have a line here?
We do the adjoint on both?
Excellent, excellent. Thank you, Jesus. We need to do the adjoint matrix, and then we go through Gauss-Jordan, and we're going to convert the adjoint matrix to a different kind of adjoint. On the left, we're going to do Gauss-Jordan. So A turns into row reduced row echelon form. And the right side, whatever happens, we don't care. We're going to call that the inverse. So that's our plan, right? So with that in mind, we're going to go to Symbol Lab. So I'm going to stop this share. I'm going to start another share. And this time we're going to Symbol Lab. Okay. Now for Symbol Lab. All right. So hopefully everybody can see my Symbol Lab here. We're going to do Gauss-Jordan. And our matrix it's going to have 3 rows and how many columns?
3 by 3, isn't it? Oh no, never mind, because it's adjoint. So is it 3 by 6?
All right, it's going to be a 3 by 6, right? And you will see why in a moment. The first 3 by 3, that block is our matrix of coefficients. So we're going to input the numbers 3, 2, 5. Excuse me. Okay. Okay. Now, that's 3, 2, 5. And then the second row is 2, 2, 4. In the third row, -4, 4, 0, right? That's the coefficients. And here I'm just going to input a 3 by 3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Is everyone with me on this one? Okay, so this is what we call the adjoint.
Yeah.
Okay, cool. And then just hit go. And there you have it. Now, let's see what happened on the left side. Remember what we were hoping for? Now, I'm going to copy this first onto my page, and then I'm going to change my share. I have 1, 0, 0, 0, 1, 0, 1, 1, 0, and then 0, 0, 1, 1 quarter, -1/8, a quarter and an 8, -5/4, and an 8. Okay, now let me switch. Okay, so I just copied what I had. This is kind of the new adjoint matrix. So what do you think? On the left side, do I have the identity matrix? Do I have the reduced echelon form? Is this the identity matrix?
We have the echelon form.
Good. We have the echelon, but it's in a reduced row echelon form, right? Remember, we want to have a 0 up here. And look, we cannot get this in the reduced row echelon form, right? Look at this last row. Would you agree a 3 by 3 identity matrix? We were expecting this, weren't we? Shouldn't we have gotten this? Look, we got 1, 0, 0, 1, 0, 1, 0, And then we needed 0, 0, 1, but we have 1, 1, 0. That row of zeros. Therefore, here, this is what I'm going to write. Cannot form I3. We cannot form, this is what I3 looks like. We cannot form this matrix. Therefore, no inverse. In other words, A inverse does not exist. We call that matrix A. A is a singular. That means when you try to solve this system, remember the solution to system is A inverse B, isn't it? If it's singular, what am I going to do here? Nothing we can do. Exactly. So this system doesn't have a unique solution, right? This does not have a unique solution.
Yeah.
Okay. Everyone okay on this example that we did? Now let's do one where it works out, just so you see, okay, well, I see one that doesn't work. How about one that works? Let's change my share and we go to the book. Let's take a look at the number, for instance, number 20. There you go, number 24. Let me write down number 24 on my paper. So number 24 is 132,005 and 005. Okay. We want to find the inverse. So I'm going to go to a symbol lab. And in symbol lab, we're going to input our matrix, right? Again, I'm going to have, I'm going to do a Gauss-Jordan of a 3 by 6. Okay, so it's going to go first. The first row of A is 1, 0, 0. And I'm going to go ahead and put the identity matrix on the other side. Remember, this is the adjoint. Then the second row of A, the numbers are 3, 0, 0. The second row of the identity matrix is 0, 1, 0. The third row of matrix A in the exercise is 2, 5, 5. The third row of the identity matrix is 0, 0, 1. Now let's do Gauss-Jordan. And what about this one? What do you think? Look at just this 3 by 3. Does this one have an inverse?
It doesn't have an inverse because there's 2 ones on, I think you call it the second row.
Right.
Column.
Exactly. And look at the third row, 0, 0, 0. We expect again a 3. So this one again, A is singular for this one, right? Doesn't have an inverse. Darn it. Let's find one that has an inverse. Let's go back to the book. I'm going to look at the number 16. Okay, let's do number 16 here. Let me write it down. Number 16, the numbers 10, 5, -7, -5, 1, 4, 3, 2, -2. Okay, let's see if this one has an inverse. Okay, let's go with this one now. 3 by 6. The first row of number 16, 10, 5, -7, 1, 0, 0. That's the first row of the identity matrix. Then -5, 1, 4, 0, 1, 0. And the third row is 3, 2, -2. And the third row of the identity is 0, 0, 1. Did I input those correctly? Does everything look okay? I guess it looks okay. All right, let me hit go and please have an inverse. Yes, there you go. You see that nice reduced row echelon form, right? Identity matrix 3 by 3. The numbers you see on the right side, folks, is the inverse of this matrix. So I'm just going to write it in my notes so I have it for reference. A inverse is going to be -10, -4, 27, and 2, 1, -5, -13, -5, 35. Good. Now, let me go to matrix calculator. What do you think should happen if I multiply? I'm thinking number 16. I want to check the answer. What do you think should happen if we multiply A 10, 5, -7? Oops, sorry. 10, 5, -7, and -5. 1, 4, 3, 2, -2 by matrix B. Remember, this is our inverse. And what do you think is going to happen when we multiply them? A matrix multiplied by its inverse.
You get the identity matrix.
Perfect. Thank you. Let's see if we do. If we do, we will take a break. If not, no break for us. All right, holding my breath here. Make sure I copied everything right. Okay.
Please be right.
Thanks. And here goes nothing. There you go, ladies and gentlemen. You see that? Isn't that beautiful? So that's how we can check. Now, if you check, if you switch the order of multiplication, we do BA. Let's see. No, it's still doing that. I wonder what the error is. Swap matrices. Okay. Oh, we did. Now let's multiply them now. I'm changing the order of multiplication. Yes, you see, it still works. So we just showed A inverse A inverse. Either way uses the identity. So perfect. We earned our break this time, ladies and gentlemen. Is everyone okay on what we have done in this section?
Yeah.
Perfect. Did we earn our break? I hope. Okay. So then is it okay if we do take a break, everyone?
Yeah, we're good.
We're good? Okay. Awesome. So okay, so let's continue on. And hopefully you all can see a page of the book now. Let's see. Okay, so we are in section 2.4, and again, I have a page of the book up here. Now, section 2.4 pretty much is the end of this chapter for us. We do have a section of applications, which I really like to get to this evening, but if we don't, it's okay, but I'm going to try to get to it Anyways, so let's look at section 2.4. In section 2.4, we're going to talk about elementary matrices, and the objective here is simple. You see the objective here, I'm just reading those, is that we want to factor the matrix into product of what we call elementary matrices. Now, you'll see a formal definition down here of elementary matrix in a moment. So we're going to look at two factoring methods, okay? The one that's really interesting is the LU factorization. So that's kind of where we want to go with this. The L stands for lower, U stands for upper. So we have lower and upper matrices. Okay, now here's the definition of what is an elementary matrix. Okay, so an elementary matrix, remember, these are all square matrices, so they're order n. These are n by n. It is a matrix that you obtain or you get from the identity matrix. So if I have an I sub 3, that means I have a 3 by 3 identity matrix. And you get a new matrix called elementary matrix when you perform a single elementary row operation on the identity matrix. A single operation, okay? Not 2, not 3, just a single operation. Now remember, elementary row operations, we had 3 of them, correct? Those elementary row operations, again, just to recall, what is it? We can switch rows, right? That was one operation. And we can multiply any row by a constant, right? A non-zero constant. That's elementary row operation number 2. And the third one is you can add a constant multiple of one row to another row. So those are the 3 elementary row operations. Therefore, we have 3 types of elementary matrices as a consequence, because remember, these are done on elementary row using elementary row operations. So maybe let me switch to my notepad and I'll actually show you a few examples of my own here. Okay, so we're talking about elementary row operations, folks. All right. So for instance, in this example, let's take a look at elementary matrix. In this example, E for elementary matrix, I have 1, 0, 0, negative 3. Remember, this is a 2 by 2 identity matrix. I should say it's not. It used to be before I did something to it. So what do you think happened to the identity matrix? I did a single operation. What do you think I did to the identity matrix to get what you're looking at? Shouldn't this be 1 for an identity matrix, order 2?
Yeah.
Oh, okay. So how can I get a negative 3 then? This was 1. What did I do?
Factor out a negative 3.
Okay. Now remember, elementary row operation, we can switch rows, we can multiply a row. So didn't I multiply the second row of the identity matrix by negative 3?
Oh, okay. Yeah.
Right. We got to think in terms of those elementary operations. There are 3 elementary row operations. So we're supposed to think in terms of those. Again, these are switching rows, multiplying a row by a constant, and then adding a multiple of a row to another row. So this is what they call a type 1 elementary matrix. Type 1, you simply multiply any row of the identity matrix by a constant. There you go. That's it. This is an elementary matrix now. See how simple? A single operation. Okay. Now, here's another one. Call this E1. This is E2, a separate one. I'm thinking a 3 by 3 identity matrix now. Now, tell me, what do you think I did in order to get this matrix from the identity matrix? I did a single elementary row operation. So what do you think I did to get the 3 there? Remember, this is 1, 1, 0. The identity matrix is 0, 0, 0, 0, 0, 0. I have a 3 here. What do you think I did to this identity matrix to create a 3 here?
You multiply by 3? Or, oh, wait, never mind.
That's okay. See, you can't say I multiply first row by 3. Because remember, here's the identity matrix. If I multiply first row by 3, this should become 3, right? Not this one. So I did not multiply by 3. Not the first row anyway. How can I get a number here? This number that appears in here should come from the third row, shouldn't it? Somehow, when I combine rows. Okay, so let me give you the answer. What I did was this. I multiplied 3 times the third row and then added it with the first row. Look, 3 times the third row. That's 3 times the third row. And the first row of the identity matrix is 1, 0, 0. And then add them. Don't I get 1, 0, 3? So there it is. So for this one, I did 3 times R3 plus R1. See, that's a single elementary row operation I did. So this is an elementary matrix. That's type 2. This we're going to call type 2. Now, the third type, type 3, remember there are 3 elementary row operations. I multiply by constant. I added a constant multiple to another row. The third elementary row operation is when we switch rows, right? So check this one. This is the third one now I'm doing. I'm thinking a 4 by 4 identity matrix. And you tell me, what do you think I've done here? I did a single operation. How can I do a single operation? And a 4 by 4 identity matrix is going to look like this. What do you think I did? Here's the 4 by 4 identity matrix. Correct? Compare this one to that one and see if you can determine what it was that I've done. Row 1 looks exactly like row 1. Row 3 looks the same, doesn't it?
Yes.
Now look at row 2 of identity, row 4 of this one. Look at row 4 of the identity. Look at row 2 of this one. So what do you think I did? A single operation.
I don't know if I might be looking at it right. Did you switch that? Well, I don't know if switching is like an actual operation.
Yes, it is.
Oh, okay.
You got it. Remember these elementary row operations again. You can exchange, interchange, or switch any 2 rows. And that's what I indeed did. I switched row 2 and row 4. a single operation. So yeah, this is elementary row operation. This is elementary row operation, constant multiple of a row. And this is elementary row operation. You add a row to a constant multiple of another row. So those are the three elementary row operation. So every one of these matrices is called an elementary matrix. Okay, now let's look at this one example that I have. In this example, I made up a matrix A. Matrix A is 1, 2, 1, 0, negative 1, 4, 2, 3, 4, and 3, 6, 0. E, this matrix E, that's when I multiply 3 times row 1 and add it to row 3 of the identity matrix. And I'll write it down for you in a moment, what I'm doing here. So this is the elementary matrix. And how did I get this? I did 3R1 plus R3. That's what I did to get this elementary matrix. Okay. So I did 3R1 plus R3 of I3. That's just E. Has nothing to do with this. That's just what I did to E. Now, if I do E times A, what am I gonna get? E is 3 by 3. A is 3 by 4. So the product is gonna be a 3 by 4 of EA. So I'm gonna multiply the first row of E, the first column of A. First row, first column. It's gonna be 1 times 1, that's 1. 0 times 2 is 0. 0 times 1 is 0. You add those, you just get 1. Okay. Now, likewise, I'm just going to write this now. Remember, these products we can do using technology. We don't need to do them by hand. I just want to show you how I'm getting these numbers. If you actually do E times A, that's, if I did that right, that's what I get. So for example, this one, this is the third row EA, for example, in here. This is third row, third column, 10. How did I get a 10? I did the third row of E, third row by third column. Third row, 3 times 2, 6. 0 times 3, 0. 1 by 4, 4. 4 and 6 made 10. So that's how I got these numbers. Okay, now here's what's interesting. It's like, what's the big deal? With the matrix EA you see here, this would be exactly the same matrix. The same if we add 3R1 plus R3 of matrix A. Isn't that cool? Now, check this out. I'm gonna actually show you this. So here's matrix A. First row, I'm not doing anything. Second row, I'm not doing anything. Now, it's the third row, right? Look at the elementary matrix. See, I manipulated the third row, so I'm gonna do the third row here. I'm gonna go 3 times row 1. That's 3 times this row. Add it to row 3. Add it with this row. 3 times this plus this. 3 times 1 is 3 plus 1. 4. 3 times 0 is 0 plus 4 is 4. 3 times 2 is 6 plus 4, 10. 3 times 3, 9 plus 0 is 9. You see that? These are exactly the same. So you can get same results by multiplying the elementary matrix times A. And it's as if you're doing exact same operation with the original matrix. Okay. Everyone good on this basic example? So hopefully now we can understand this.
Yeah.
All right, thank you. Let's take a look at now this next theorem. Let me go to the book, and there you go. Okay, this is going to be theorem 12. There you go. So in theorem 12, it reads, let E be elementary matrix obtained by performing an elementary row operation on I, an M by M identity matrix. Remember, it's a single operation. Okay. If that same elementary row operation is performed on an M by N matrix A, the resulting matrix is given by product EA. So that was just the example I showed you as illustration of this theorem. So everyone okay with this theorem? Okay. Now, let's continue on. Now, this is actually an interesting example. Let me real quick go over this for what's coming. So here's a matrix A. What he's doing, the author here, is going through elementary row operation, okay? And it's gotten this matrix to where there is a lower triangular formation of 0. In other words, he wrote the matrix in this Gaussian form, right? This is Gaussian, not Gauss-Jordan, because you don't have zeros above 1. So this is the Gaussian form. Now, on the right side here, in the middle, it tells you the operation he's done. Okay, so he says first, I switch row 1, row 2. That's what he did here of the original. That's what he gets. Now, he's doing exact same operation on the identity matrix. So he's creating a series of elementary matrices here, right? So here's E1, switch row 1, 2, he did it with the identity matrix. Go back to the original. What does he do next? He says, well, I'm going to do negative 2R1 plus R3, that's elementary row operation. Replace row 3. Okay. And he gets this. He's going to do exact same operation with identity matrix. This E2 has absolutely no correlation with E1. Okay. So it's a whole new identity matrix. So if you get a brand new 3 by 3 identity matrix, you add the third row plus negative 2 times row 1. This is what we should get. He goes on to this side. He says, okay, well, let's see. He got 0, 0, 0 now. What does he do? Oh, he's doing half times row 3. You see, it's 2, negative 4, row 3. He wants to get 1 here. This one. So he multiplies the third row times a half. And then this is the third row times a half of the brand new identity matrix. E3 has no correlation, no association to E2. E2 has nothing to do with E1. These are independent elementary matrices. So each time he does something on the left, he does the same operation on the identity matrix. So everyone hopefully follows what he's doing here. Now, here's the punchline. So he has 3 elementary matrices here, E1, 2, 3. And this is what's fascinating right in here. It says, instead of doing what he did to the original matrix, he can do now E3 times E2 times E1 times A. And he's actually shown you now. Here's E3. He's doing backward. E3 times E2 times E1 times the original. the original A, not this one, the original A. And he multiplies, we use software, he probably used the same thing. So he multiplied this one times this one. Here's the result. This one times the one next to it, here's the result. This one times next to it, this is the final result. Now, look at this matrix and look at this matrix. You see how they look the same? This is matrix B. So matrix B is in Gaussian form. So he wanted just to get Gaussian form. So he could have done it using these elementary matrices. Okay. So this is matrix A, the original, and this is the Gauss form, right? Notice the Gauss form, you have lower triangular 0. True, that's Gauss. And these two matrices are equivalent matrices, aren't they? They're equivalent because, look at this, we use the series of elementary row operation. This matrix is equivalent to this. This one equivalent to that. This middle equivalent to that, because we followed elementary row operations. Okay. And then now he's defining the row equivalence here using elementary matrices. So remember, B is a row equivalent to A. So this definition says, suppose we have two matrices. This matrix B, that would be this one, is row equivalent to matrix A when there exists a finite number of elementary matrices so that you can multiply them by A to get B. That's like the formal definition of row equivalent matrices. Okay, nothing earth-shattering here. It's just like, wow, that's cool. Now, this theorem tells us that elementary matrices are invertible. In other words, their inverse exists. Okay, so the existence of inverse of elementary matrices is guaranteed by this theorem. Okay, now let's see how we're going to get these inverse matrices. Look at this elementary matrix E1. And he tells you here what he's done. So he says, I switch row 1 and row 2. Remember, you do only a single operation. Now, inverse of this is like undoing it. When you go inverse of elementary matrix means you kind of undo what you just did. So to undo, if you switch row 1, row 2, to undo that, don't you switch R2 and R1? So there you go. The inverse of this operation, inverse of E1, is when you switch row 1, row 2 of the identity matrix here. Look at this one. This elementary matrix, it says, I got this matrix by multiplying -2 times row 1, adding it to row 3. So the inverse of this operation is going to be 2 times row 1 added to row 3. Notice the effect is to change -2 to 2 here. When you switch rows, you don't see a difference here. This one, you see a difference. So we can kind of make this like in general. If you want the inverse of a matrix, elementary matrix, when this is something other than 1, just rewrite it in the same position, change sign. Make it opposite. And that will give you the inverse. Or you can go to, to the software and try it. But this is easier this way. Look at this one. He said elementary matrix 3. That's when I multiply the third row by half. What's the inverse of that operation? You multiply by 2. See this? That's the inverse of this operation. So you multiply third row by 2, if you multiply any row by a constant for the elementary matrix, you do reciprocal of that for the inverse. So he's showing you how to get the inverse of elementary matrices using elementary row operation, constant multiplication, switching rows, and adding a constant multiple of a row to another row. Okay, so that's how we're going to find. Again, you have two choices, folks. You can do it this way, or you can go to the software and say, you know, here's my elementary matrix. What's the inverse? Just put it in, hit the inverse, and you will see you get, this is much faster. Okay. Now, here's a property. Theorem 14 gives us the property of invertible matrices. A square matrix is invertible if and only if it can be written as product of elementary matrices. This is, again, it relates the existence of inverse matrix as it relates to elementary matrices. Okay. So we don't do much with this theorem, honestly, but it just, again, there is a connection there. Now, let's take a look at this example, and then we'll look at our own in just a few moments here. Actually, we'll do our own in just a few moments. Let me skip this one. It's just good that he has all the numbers here side by side. Okay, actually, let me go through this. Sorry. Okay, so here's matrix A. It says find a sequence of elementary matrices whose product, the product of which gives you A. So in other words, it's down here, elementary matrix E1, inverse, E2 inverse, E3 inverse, E4 inverse. See the product of them gives you the original A. It says find these. So to find the inverses, first, we need to get A to be in this Gauss-Jordan form. See that identity form, Gauss-Jordan. So you go through these elementary row operations to do that. And then at each stage, you create an elementary matrix for that row operation. So for instance, in this matrix, he says, I'm going to multiply first row by -1. So this is -1 times the identity matrix. So that's E1, elementary matrix 1. And then he goes down here. He's got his 1 leading 1. He needs to get 3 to become 0. He says, I'm going to do -3 times R1 added to R2. And then he gets this. Well, he's going to do -3 times R1 added to R2 of an identity matrix 2 by 2. This is what you're going to get. Then he does next one, half times R2. He does half times R2 of an identity matrix. And finally, to get the 0 above 1, he says, I'm going to do -2 times second row added to the first row. He's going to do exact same thing to the identity matrix. Remember, there is no connection between E1, no connection between E2, E3, E4. Every time you do a row operation, you create a brand new elementary matrix from scratch, from the identity matrix. Now, if you multiply E4, E3, E2, E1, A, you get the identity matrix. Okay. It says solve for A to obtain this. Well, how do we solve for A? You multiply both sides, right, by the inverse of this. Let me show that on my paper for you, folks. This part I'm going to show. So let me write down first, and then I switch to my pad. Okay, so I have E4, E3, E2, E1 times A equals identity. We want to solve for A. And it says A is E1 inverse, E2 inverse, E3 inverse, E4 inverse. That's what it turns out to be. Okay, so I want to show you how he gets that one. Okay. Let me switch to my, what you call it, to my notepad here. Okay. So this is what we want to solve here. This one. Again, this is solve for A, right? Now, all of these form a matrix, right? It's a matrix product, E4, 3, 2, 1. So if I pre-multiply by E4, E3, E2, E1 inverse times, I'm doing the left side, pre-multiply by its inverse, E4, 3, 2, E1. A, I'm pre-multiplying the identity matrix on the right by exactly the same thing. So it's going to be E4, 3, 2, 1, inverse I. Okay. Now, on the left side, is in any matrix inverse times the matrix identity. This product is going to give you the identity matrix. Right? So that's just A. On the right side, earlier we had a property of inverse matrix. Remember AB inverse? Let me write that one. This is from previous section. What is AB inverse? Isn't that B inverse, A inverse? This is from previous section, right? This is from section 2.3. Now, let's apply this to what's down here. So when you do the inverse of a product, you do product of inverses in reverse order. So in other words, this, I'm going to do it in reverse order now. It's going to go E1 inverse, E2 inverse. You see, I'm going in reverse. E4 inverse times identity is itself. So there you go. That's how he solves it and gets this. Okay, just want to show you how that matrix manipulation works. Okay. So now let's go back to the book. All of this is leading to something, right? It's like, okay, where is this going? All right. Now, okay. So having gone through all of this, folks, this theorem 215 is a very important theorem in our work. This theorem actually has about 20 parts. 20. You're looking at 5 parts for now. By the time we get through this course, you will see all 20 parts of this theorem. Okay, so it will continue on to chapter 3. This theorem will continue to chapter 4, and then it will go to chapter 6. So this theorem, it's a huge theorem in linear algebra. Okay, so let's take a look at this theorem a little closer. In chapter 2, we only are concerned about 5 out of 20 parts of this theorem. It may even honestly be more than 20. I'm going from memory here. But you will see. You can correct me near the end of the course and say, by the way, that wasn't 20, it was 22. But it's at least 20. I know that one. Okay, so let's read this theorem. In this theorem, it reads, if A is n by n matrix, so we have a square matrix, then the following statements are equivalent. Now, what does that mean? That means these 5 statements are either all true or they are all false. If one of them is false, everything else is false. Okay, so the first part, okay, so matrix A. If A is invertible, that means it has an inverse, right? Okay, if A has an inverse, that's number 1, then it follows that AX equal B has a unique solution. It follows that the solution to homogeneous system, number 3, AX equals 0. The 0 on the right side here, folks, this is a matrix of 0. This one is a matrix of 0. The solution to the homogeneous system. The homogeneous system has only trivial solutions. That means x1 is 0, x2 is 0, x3 is 0, x4 is 0, x5 is 0. You get the idea, right? The system that's set equal to 0, a linear system set equal to 0, if A is invertible, the only way that can be 0 is if all the x's are 0. Now, number 4 says A is row equivalent to identity matrix. And remember when we did Gauss-Jordan of A, didn't it look like identity in the end? It did, didn't it? Remember when we did the adjoint? The left side was identity matrix. So that's what this says. And finally, for now, number 5, A, matrix A can be written, and this is, there we go. This comes from this section. It is possible to write A as product of elementary matrices. So, what do you think, folks? Does that sound cool, or any reactions to this theorem other than being cool? Again, this is a very long theorem, but for now, there you go. So if I solve a matrix, okay, let's say they give me a system to solve. First thing we do, let's say, is find the inverse. If the inverse exists, it means all 5 of these are true. That means, oh, okay, then I have a unique solution. If B, here this B, is not a 0, homogeneous 0. But if I have AX equals 0, the only solution to that is going to be all x's are 0 if A is invertible. So we can cite this theorem and we can just say, well, A is invertible, therefore 3 follows. Okay, now the proof of this, okay, the proof of this, we are kind of short in time. It's really cool. I had it on my agenda, honestly, to prove this for you. And the way this proves is the following. This is how I was going to do. I was going to show that number 1 implies number 3. If number 3 holds, it implies number 4. Number 4 implies number 5. And number 5 implies number 1. The only one I didn't call was number 2. That was my agenda to prove this. Okay. Now, proof of number 2, actually we have done, right? We did this proof earlier. Remember, we said this has a unique solution. I actually went through it, pre-multiplied by A inverse. So you saw the proof of this, but you didn't see the proof of the other ones. So I'm going to skip the proof of these, okay? And let's see. Let's go to LU factorization here then. Okay. Now, the LU factorization, the idea here is this. First, what are L and U here? You're looking at a lower triangular matrix, 3 by 3. This is the L in the LU factorization part. L means lower triangular. A lower triangular matrix has numbers only in the lower part. See, above that, you have this triangular formation of zeros. So this is L, means numbers are on the lower part. If the numbers are above the diagonal, then you have upper triangular. Okay, so here's L, and this is U. And here's a definition of LU factorization. If a square matrix can be written as product of lower triangle L and upper triangular U, there you go. A is equal to LU, then they call that LU factorization. In a way, because L multiplies by U, right? Remember, what are factors? Like when we say factors of 6 are 2 and 3, it means 2 times 3 is 6. Well, the product of L and U gives you A. So that's why this is called LU factorization. Okay, now, here is the process of LU factorization. But don't worry about this process again. We're going to do this using the software, okay? But it's good to kind of see all the process that you go through. It's really a lengthy process. Look at finding the LU factorization here. What's involved here, folks? This is matrix A. So you're going to row reduce the original matrix, and here is your upper triangular matrix, right? We have numbers above the diagonal. So this is the U part. The reduced matrix U above is upper triangular, this one. And then you keep track of elementary matrices here. Okay. Now, if you do E2, EA times A, E2, E1 times A, you get the upper triangular. And if you solve that equation, A is this. And the product of lower triangular matrices, you multiply the inverse. Again, don't worry about this. We're not going to do this by hand, folks. We're going to use that software in a minute. So you get the LU factorization. It's a really tedious process. You really don't do it by hand. Okay. Now, here's something interesting, though. The LU factorization, by the way, folks, is very, it is an efficient way of solving system. Why are we doing this? Here's why. We want to solve a system. We solved the system earlier, didn't we? Using the inverse matrix, right? We saw at least one example. We're doing exactly the same thing. We're doing it using LU factorization. And I'll explain in a moment why this is a better way of doing it, even though it looks so tedious. So first, we want to solve the system. Notice in this solution, numbers 1 and 2, there is no inverse involved. So that's the beauty of LU factorization to solve a system. You do not get involved with the inverse of a matrix. So first, you need to write y equal upper triangle times x, solve the system, then solve this for x, the column matrix X solution of original system, because this is this. Okay, again, seems like a tedious process. Here's an example of this LU factorization to solve, and then I'll explain why this is efficient versus inverse matrix. So here's a system. He's doing exactly, by the way, numbers 1 and 2 now. What he says here, he's actually showing you. This is the system AX equal B. So obtain LU factorization. So, and I'm sure he's used a software himself to do this honestly. Notice this is L because you have numbers below the diagonal. This is U. You have numbers above the diagonal. So you have L, U. So the first thing is to obtain the factorization. One of the programs that I go back to, you see, it will do LU factorization for you. So this is going to be done for us. Now, check out the next step. He says, let y be upper triangular times x. So here's the solve the system for y. And so here's the system. This is actually L, isn't it? This is L, y equals B. Remember, this is B. And he's multiplying this matrix, that's the L, times y to get B. Right in here, you see that? Sorry, this is right here. This Ly, lower times y equal B in here. So you can solve the system. We can do this using Gauss-Jordan. Okay, so we solve the system, and this is how he solves it. These are the solutions to, here's y1, here's y3, and this is the solution to y. So let's say we can get the solution from the software. Now, once we have the solution to y, remember this is Ly equal B. It says now solve the system ux equal y for x using back substitution. Okay, ux, so this is now the upper triangular matrix, the upper times x. So the lower times y equal to constants, the upper times x equal to y's. You solve for x, and this is the solution to the system. Okay, now let's see how we're gonna do this. Oh, the reason, by the way, folks, again, this seems like crazy way to do it is because when we do inverse multiplication, when we do inverse of a matrix that is like, let's say large matrix, say 30 by 30, if we do it using methods of chapter 3, which is using cofactor expansions. We talk about those next week, possibly. If we do those methods of chapter 3 to find the inverse, and it's going to take unbelievable amount of operation, something he has it. Let me go to page 116 here and show you. This is worth looking at. There you go. If we want to do cofactor expansions and determinants to find inverse, again, for the 30 by 30 matrix, look at how many operations are involved here. 10 to 30 second operations. And check out this paragraph. That's amazing. It reads, if a computer could do 1 trillion operations a second, it would take more than 1 trillion years to compute the determinant. And that's what is done in order to find the inverse. So these processes are just unbelievable when it comes to larger systems, how much resources they use. So the LU factorization, make a long story short, LU is preferred method. Okay, now let's actually look at maybe a couple of examples here. First, the LU part. These are applications. Hold on. Okay, section 2.4. By the way, we're done. That was at the end. Result of this section is what you see here. We'll do an example in a moment, but let's go through some basic ones, and then hopefully we get to the solving system using LU factorization. The first part, determine whether the matrix is elementary. If it is, a state elementary to operation used to produce it. Okay, so numbers 1 through 8, for example, is number 2 an elementary matrix? What do you think? Remember, elementary matrix is a matrix that is obtained when you conduct a single operation on the identity matrix, right? So, is number 2 an identity matrix? What do you think? What do we know about identity matrices, by the way? Like I2, I3, I4. Anyone?
I think, well, I'm not sure specifically relating to this. At least like how you were kind of talking about it. It'll give you like a different like it'll be like 2 by 2 or 3 by 3.
Very good.
So that
Exactly.
might help.
Yes, absolutely. So number two is not an elementary matrix because it's not a square matrix. That rules it out right away. Remember, elementary matrices are square matrices. So 2 cannot be elementary simply because it's a 2 by 3. Now, numbers 1, 3, 4, all of the other ones are square matrices. They could be. So for example, what do you think of number 6? Is number 6 an elementary matrix? Did he get this matrix by performing a single operation on a 3 by 3 identity matrix? How did he get the 2 here, you think? What did he do to the identity matrix 3 by 3 to get a 2 here?
Could he, well, I don't really know if, because I was like, well, it could have been something along the lines of like doing the 2 like multiplication, but like something where like taking the original like the 0, 0, 1. But I don't think we can do that because we have to work with like just this base matrix, right?
You're right. It has to be. He has to start with an identity 3 by 3. So it's got to be 1, 0, 0, 0, 1, 0, 0, 0, 1. What can I do to that and create a 2 in this spot? Third row, first column.
Oh, I don't know if, well, I think you could maybe just add row 1 twice.
Very good. Multiply row 1 by 2, add it to row 3. Remember, the original row 3 is 0, 0, 1, right? So if you do 2 times row 1, add it to row 3 of the identity matrix, you're going to get 2 exactly in that spot. So yes, number 6 is an elementary matrix. Okay, so there you go, number 6 it is. Now, let's go further south, A, B, C, or D's, and let's skip these. Let's see something that we might want to be doing. Let's take a look at, wait, these will, okay. These elementary matrices, let me skip these. We're not going to do much with elementary matrices later on, so I'm going to skip these. Let's see. How about, let's go to an LU factorization. I'm going to skip over all of these elementary matrices and inverse elementary matrices and all that. Let's go to an LU factorization. And there you go. These are numbers 41 through 44. Okay. So it says in exercise, find the LU factorization. Now, I'm going to write down, let's do number 44 together. I'm writing down 44 on my paper, and then we're going to go to the software and actually have the software do it. 0, 1, 3. Okay, so this is number 44. Okay. 2, 0, 10, 0, negative 3, 12, 0, 1, 3. Now, here's where I'm going, folks. Stop the share and share this one. Okay. All right. We want to do LU factorization, right? Now, you see this one? LU decomposition right there. So we have a 3 by 3. Let's clear. I already have matrix A up here, 3 by 3. See the brush here? It says clean it. That's how you clear all the entries. I'm inputting exercise number 44 in it. Here's 2, 0, 0. 0, negative 3, 1, 10, 12, 3. We're good. Now, hopefully everyone's with me. And then here's LU decomposition. I'm just going to hit or click on LU decomposition. Boom. There you go, folks. Here's your LU decomposition. See, this is the detail. Here's the lower triangular matrix, right? I mean, you got the numbers. Oh, I'm sorry. This is the original. So this is the L. Remember, L means you have numbers below the diagonal. That's the L. This one next to it is the U. U means upper. You have numbers above diagonal. See the one here? So I have L and U. So this is the LU decomposition. Are we okay on this one?
Yeah.
Perfect.
Yes.
Beautiful. So that's all we want to do on this one. Now, let's actually, so that's all. I mean, if you can do this using elementary matrices, it'll just take a long time. And it's really done this way much better, as you can see. So now let me go back to the book and we do one example and we'll be done. I'm going to stop share. I actually want to use LU decomposition now to solve a system. So since we know how to do that using the software, and don't worry, you don't have to do this by hand on the exam either. So here we go. Now they don't have too many exercises here. He just has a couple. So let's take a look at number 46 together. In number 46, it says solve the system by part A, find LU factorization. So again, I'm going to write this on my notepad. So this is exercise in section 2.4, number 46. We have 2x1 equals 4. Negative 2x1, 6x1, negative 2x1 plus x2 minus x3 equals negative 4. Below that, 2x2 plus x3 equals 15, and x sub 4, negative x sub 4 is negative 1. Okay. Now, in part A, it says find LU factorization. Okay, let's go to what you call it. Let's go to that software. Where are you? Software here. Cool. So I'm gonna go now. This one, what do I need to type in? Let me clear this. What should I type in? Remember, we need to have a square matrix here. That's the matrix of coefficients, correct? So the original matrix is going to be what? It's going to be a what size? 4 by 4, correct? Because we have x sub 1, x sub 2, x sub 3, x sub 4. Oh, how did I do that? In case you weren't watching, if you hit plus here, it goes adds, see, makes it bigger, bigger, smaller, smaller, smaller. 2 by 2 is 1 by 1. So we want 4 by 4. There you go, 4 by 4. So what will be the first number here? 2. Remember, these are the coefficients, the matrix of coefficients. So it's going to be 2, 0, 0, 0. Because the first equation is 2x1 equals 4. The second equation is negative 2. Next number is 1, negative 1, and then 0. Correct? And what is the third row going to be? 6, 2, 1, 0. And the fourth row, we're only looking at the coefficient, folks. Don't look at what's to the right of equal signs. The fourth row is going to be what? 0, 0, 0, negative 1. Correct? And we're going to do the LU decomposition now. There you go. Boom. Here's your LU decomposition. So I'm just going to write these down now. So matrix A is LU. I'm copying the matrix down. This is going to be 1, negative 1, 3, 0. 0, 1, 2, 0. 0, 0, 1, 0. 0, 0, 0, 1. And the U, the upper matrix, matrix 2, 0, 0, 0, first row. 0, 1, negative 1, 0, 0, 0, 3, 0, and 0, 0, 0, negative 1. Everyone okay on that one? Okay. Now let me go back. Sorry, I keep switching back and forth, but I want you to see all the components of what I'm doing here. Okay, so we just did part A. Everyone okay on part A?
Yeah.
Perfect. Let's do part B. Now it says part B, solve the lower triangular system. There you go. He's guiding us through. He says do Ly equals B. Okay, Ly equal B. Now let me write these actually, and then I just stay on my notepad. In part C, solve Ux equals Y. And okay, let me go to my notepad and we'll finish it on my notepad here. Good. So this is, hopefully this is kind of what you have on your notes. Okay, first we need to solve Ly equal B. So what does that look like? Remember, L is this matrix, right? This is L and this is U, right? You have a lower, this one is upper. Okay, so Ly, that means I'm doing 1, negative 1, 3, 0, 0, 1, 2, 0, 0, 0, 1, 0, 0, 0, 0, 1. That's L. What does Y matrix look like? It's a column matrix. It's Y1, Y2, Y3, Y4. Equals B. B is a matrix of constants. So B is this column matrix 4, negative 4, 15, negative 1. Sorry, my 4 looks kind of weird. Okay, so that's what the right side of this is. I'm just going to write a better 4, negative 4, 15, and negative 1. Okay, so here's L, Y equals B. Now, I need to solve this one. Okay, when you solve this one, let's see. Doesn't the first row, first column, doesn't the first row say y1 is 4? True, when you multiply first row, first column, don't I get y1? That's 0, 0, 0. So from this, we get y1 is 4, correct? From second row times this column, negative y1 plus y2. What should that equal to? Negative 4. Third row times this column, 3 times y1, 2 times y2, 1 times y3, 0 by y4. So that's 3y1 plus 2y2 plus y3 equals 15. And finally, the fourth row, 0y1, 0y2, 0y3, 1y4. y4 is negative 1. Okay, therefore, we have these solutions. I'm going to write them. y1 is 4. y4 is negative 1. Isn't y2 negative 4 plus y1? y2 is negative 4 plus y1. So y1 is 4. Therefore, that's negative 4 plus 4. Y2 is 0. And y3, now I can go to this long equation. 3 times y1 here, plus 2 times y2 plus y3 equals 15. This is 12, subtract 12. I hope I did this right. y3 is 3. Therefore, the Y matrix, y1, y2, y3, y4, is going to be 4, 0, 3, negative 1. Is everyone okay on this work, everybody? We are almost done. We've done the hard part. We're good with this. That's the answer to part B. And we are about to part C. Part C actually will help us solve the system now. In part C, if everybody's good on part B, in part C, we have to do UX. This is U. X is the matrix of variables, x1, x2, x3, x4. Equals Y, we just found Y. So I'm going to bring those three pieces together. Part C, we're doing upper times x equals Y. The upper matrix, upper, again, is this one, folks. I'm using this one. And we are almost done. Sorry, we're at 9 o'clock. We got 2 minutes. We'll be done, I promise. So here's the upper. 0, 1, 0, 0, 0, negative 1, 3, 0, 3 zeros, negative 1. X is the matrix of variables, x1, x2, x3, x4, and equal to the y's, 4, 0, 3, negative 1. And then you solve this one. Look at this one. 2 times x1, 0, 0, 0. So this tells me first row, first column says 2x1 is 4. Therefore, x1 is 2. Okay, how about this one? The fourth row says 0, 0, 0. Negative x4 is negative 1. Therefore, x4 is 1, right? So we got the x4, we got x1. And how about the third row? What does the third row tell? 0x1, 0x2, 3x3 is 3. So x sub 3 is 1. We're good on that one. So we just go to second row now. 0x1, 1x2, negative x3, 0x4. So again, 1x2, negative x3 equals, second is equals 0. Therefore, x2 is equal to x3. x3 is 1. And we've solved that system. So our solution is in the order x1, x2, x3, x4. Those are all ones. 2, 1, 1, 1. This is the solution. There you have it. I'm sorry, I'm kind of out of margin here. There you have it. Is everyone okay on this example?
Yes.
Perfect. Sorry about the headache, everyone. I know it's kind of late for this, but there is your LU factorization. Now we did number 46, I think. I think you're doing 45 for your homework, so hopefully this was going to help you do that. Remember to get the LU factorization, we're going to use that software. So let me, I'm going to stop recording here since we're done.